Hello, so in today's class we will look at Euler's phi function and how to find an expression for Euler's phi function using the generalized principle of inclusion and exclusion. So before going into the theorem, so let us first define the Euler's phi function, and now let A and B be any two natural numbers. So for AB belongs to N, so let us denote AB. So let us denote the HCF of A and B, and we say that A is co-prime. So A is said to be co-prime to B if HCF of AB is equal to 1. So if HCF of AB is equal to 1, then A and B are said to be co-prime. And now let us define what is phi of n. So for any n belongs to n, phi of n denote, so that is the number of integers between 1 and n which are co-prime to n. So the Euler's phi function denotes the number of integers which is lying between 1 and n which are co-prime to n. So phi of n denote the number of integers between 1 and n which are co-prime to n. So the function phi of n is called Euler's phi function, and then we have the expression for the value of phi of n using the prime factorization of n, which you have learned in number theory. So let us see that result. Okay, by generalized principle of inclusion and exclusion, actually we will be proving that result. So this is the result. So let n belongs to n and let n equal to, so p1 raised to m1, p2 raised to m2 plus etc. pk raised to mk be prime factorization. Then we have phi of n, so that will be given by n into 1 minus 1 by p1, 1 minus 1 by p2, etc. 1 minus 1 by pk. So this is the expression for phi of n using the prime factorization of n. Now we will be actually proving this result using the generalized principle of inclusion and exclusion. So for that we will be defining a universal set and we will be defining the properties. Okay. Before that, for the proof of the theorem using generalized principle of inclusion and exclusion, so we will be using the following results. So these are the results. So let x belongs to n and x less than or equal to n, then if the HCF of x and n is equal to 1, so HCF of x and n is equal to 1 if and only if pi does not divide x for all I equal to 1 to etc. k. So here we have n equal to p1 raised to m1, p2 raised to m2 plus etc. pk raised to mk. So if n is equal to p1 raised to n1, p2 raised to n2 plus etc. pk raised to mk, then if you have an x such that x is less than or equal to n, then x is coprime to n if and only if pi does not divide x. So p1, p2, pk does not divide x. Then the second result we have is for real numbers r1, r2, etc. rk. So for any k real numbers, the product 1 minus r1, 1 minus r2, etc. 1 minus rk. So when you expand this product, the value is given by 1 minus summation I equal to 1 to k. We'll have ri, then plus summation over I less than j, ri, rj varum. The next term will be minus summation over I less than j less than k, ri, rj, rk plus etc. We will have minus 1, last term will be minus 1 raised to k, r1, r2, etc. rk. So this is going to be the expansion of 1 minus r1, 1 minus r2, etc. 1 minus rk. So we will be using these two results in proving the generalized principle of, improving the expression for the Euler's phi function. So let us state it is a theorem and let us see the proof. We need to prove that phi of n is equal to n into 1 minus 1 by p1, 1 minus 1 by p2, etc. 1 minus 1 by pk. So let us look into the proof of this. Now for the proof by generalized principle of inclusion exclusion, we need to define the universal set and the corresponding properties. So here we will define our set to be the set 1, 2, 3, etc. up to n. So let S is equal to the set 1, 2, 3, etc. n. In an element X is said to satisfy a property Pi if these P1, okay, for property P1 satisfies cheyanankil, we'll take the property P1 such that P1 divides X. So if P2 divides X, we'll call it as a property P2, and if Pk divides S, that is called as property Pk. Okay. So corresponding to the K prime P1, P2, etc. Pk in the prime factorization of n, we define K properties P1, P2, etc. Pk as follows. So an element X belongs to S satisfies property Pi if and only if X Pi divides X. Pi divides X where I is equal to 1 to etc. to k. So if Pi divides X, then we say that the element X satisfies the property capital Pi. Therefore, for finding phi of n, for phi of n എന്ന് പറയുന്നത് that counts the numbers which are coprime to n. ഇനി നമ്മൾ ആദ്യമേ ഒരു റിസൾട്ട് കണ്ടു, if x has to be coprime to n, then pi must not divide x. That means x must satisfy none of the properties. So therefore the required value of phi of n will be the value of p of 0. So that comes using this result. Okay. So it follows from result 1 about that. So x belongs to S is co-prime to n if and only if x possesses none of the properties p1, p2, etc. pk. So therefore phi of n will be equal to e of 0. And now e of 0 will be omega of 0 minus omega of 1 minus omega of 2 plus omega of 2 minus etc. Plus minus 1 raised to k omega of k varum കാരണം നമുക്ക് k properties ആണുള്ളത്. Now by definition omega of 0 will be cardinality of S. Cardinality of S. S is a set 1 to up to n. The cardinality of S n ആയിരിക്കും. Now let us find omega of k where 1 less than or equal to, okay, let us write it as k number. So let me write it as omega of t where 1 less than or equal to t less than or equal to k. So we'll find the general value of omega of t. So that will give all the values of the omega 1, omega 2 to omega k. Okay. So by definition omega of t will be summation over I1 less than I2 less than IT omega of P I1 PI2 etc. PIT varum. And now the number of elements which satisfies property PI1 PI2 PIT എന്ന് പറയുന്നത് that will be the integer function n by PI1 PI2 etc. PIK. Okay, അപ്പോൾ നമുക്ക് കണ്ടുപിടിക്കേണ്ട എത്ര factors ഉണ്ടെന്നാണ്. So if it satisfies a property P1 P2 PIT, it will be divisible by PI1 PI2 PIT. So the number of such factors will be given by integer function of n by PI1 PI2 PIT. So therefore this will be equal to summation I1 less than I2 less than IT. So this will be the greatest integer function n by PI1. So this is small PI1 and PI2 etc. PIT. Now this n is now equal to നമ്മുടെ n എന്ന് പറയുന്നത് P1 raised to M1, P2 raised to M2 etc. Pk raised to Mk ആണ്. So these Pi1, Pi2, Pik will be T elements from P1, P2 etc. Pk. അപ്പം നമ്മൾ ഇത് divisible ആയിരിക്കും. So therefore you are going to get summation I1 less than I2 less than IT. So this is going to be an integer. So that will be n by PI1 PI2 etc. PIT. So that is omega of t. Omega of t will be this summation and this is omega of t. ഇനി omega of k എടുക്കുമ്പോൾ that will be omega of